Hello again, everybody. Welcome back to today's session with Pre-Calculus, and today we're going to be talking about parametric equations in Chapter 8. So previously to this, we were talking about polar equations, and now this is going to transition to something that's a little bit different, but in a way it's still kind of somewhat the same. Both of them, polar and parametric, you will see in calculus, so this is something that will be beneficial. So to begin with, to give you an idea about parametric equation, it's anything that is let's say that if you have an equation with two or more variables, if each one of those variables can also be represented by a single variable of a certain function, then those are parametric equations. So for example, if you have two variables like x and y, and this is going to be considered kind of like in two-dimension, where x is normally the horizontal and y is normally the vertical. If both of those x and y variables can be represented by another variable, usually like we denote as time for t or t for time, then that can be considered a parametric equation. So three dimensions, same thing. So if you have x, y, and z, and all three x, y, and z's can be a function of t, then that's parametric then. So to start with a formal definition, we have the following. The equation of a graph in 2D is said to be in parametric form if each coordinate of a general point p of xy is expressed in terms of the third variable, usually t. So that's basically what we were just talking about. So underneath over here, you can see that we have three examples of parametric equations. And the entire set over here for each one, those are the whole parametric equation. You can't only have just one equation. So in the first case, you can see x is equal to t squared plus 4, y is equal to t plus 2. Then you have the second equation, which the second set of equations of parametric, which is in terms of trig functions. And then you have the last one, which is going to be a little bit more unique then. Now, for example 1 and example 2, you should be able to actually solve for t, or actually get rid of t and combine the equations together so that it's in terms of just x and y. But for something like, say, example number 3, that one is a little bit harder. And sometimes what that means is that for a parametric equation, it's just not worth it to convert back into Cartesian. And so you'll get to see that somewhere down the line. But for right now, today we're going to be talking about how to graph parametric equations by converting it back into Cartesian so we know what to actually look for the graph. So here's your first example. Find the rectangular form of each pair of the parametric equations, then sketch it out. So in its first example, we have x is equal to t plus 1, and then we have y is equal to t squared. So again, keep in mind, the objective right now is to basically eliminate t so that then we can combine into one single equation for x and y. Easiest way we can do this is by doing a substitution. So for example, we're going to go ahead and take x over here. We can easily solve for t and plug it back into the y. So t is equal to x minus 1, and we're going to make a substitution. So we get y is equal to x minus 1 quantity squared. So this is going to be our actual graph then, and that technically is something that we know how to graph because this is, well, an equation from a while back. This is just a parabola that's shifted over to the right by 1 unit. So graphing that out, we are going to have something that looks like the following right here. So this is going to be the curve of our graph. Now, the parametric equation, we can go a little bit further actually by looking at the path or the direction that the point is actually going towards. If we were to kind of like look at t as time. So underneath it, let's do the following then. Let's just do something a little bit extra. So we're going to look at when t is equal to 0, we plug into the equations. We get x is equal to 1 and y is equal to 0. So that tells us our starting point when t is equal to 0, you're going to start at the point which is 1 comma 0. When t is equal to 1, x is equal to 2, y is equal to 1. So that means we're going to go to this point over here on the curve, which is, looks like it's going to be 2 comma 1. So that's when t is equal to 1 then. And you can keep going on and so on as much as you want. So you can see where does the point actually follow along the curve. So maybe just do it one more time. When t is equal to 2, we have x is equal to 3, y is equal to 4. So that gives us the coordinate 3 comma 4 then. So let's see, so 3 and then comma 4. So maybe somewhere around here if I drew it a little bit better. So t is equal to 3, t is equal to 2, and then comma 3 comma 4. So here we can now see the direction of the path that you actually take. So it looks like it's going to start at the vertex and it's going up towards the right hand side of this curve. Now, if you consider time as something that's always going to be non-negative, then people would then disregard the left-hand side. But I just drew it in just so that we can see the entire curve of the parabola. Okay, so now let's look at the second example. Same idea, but this time the algebra is a little bit different. We have now x is equal to 4 plus 3 cosine t, y is equal to negative 2 plus 4 sine t. And again, I would like to convert this into Cartesian and then sketch out what the graph looks like. So this one, unfortunately, we cannot just isolate t and then plug it into the other one, but instead we have to use a trig identity. Now, the trick here is that anytime you see cosine and sine like this, cosine for one equation and sine for the other equation, you want to think about identities because that's how you're going to get rid of the t's then. So first, we'll go ahead and solve for cosine of t. So x minus 4 is equal to 3 cosine of t. And so cosine of t would then be equal to x minus 4 divided by 3. Now, similarly for y, where you can solve for what sine of t is equal to. So y plus 2 divided by 4 is equal to sine of t. The relationship between sine and cosine is the identity cosine squared plus sine squared. So what I'll do next algebraically is we'll go ahead and square both sides, and then we can add them together. So x minus 4 over 3 quantity squared is equal to cosine squared. Then we have y plus 2 over 4 quantity squared is equal to sine squared. And now combining those two together, we now get the following then. In parentheses, x minus 4 over 3 quantity squared plus y plus 2 over 4 quantity squared is equal to cosine squared plus sine squared, which gives us 1. And that graph, we do know what it looks like. That's supposed to be an ellipse. And for this ellipse, we have the center, looks like it's located at 4 comma negative 2. Whereas the radius of x is equal to 3 and the radius of y is equal to 4. So on the right hand side, we'll go ahead and sketch out the graph of that. And just like before, we're going to also sketch out the parametric part of the equation, meaning like, the path that it takes on that curve. So let's see, we're going to go to 4 comma negative 2. So that's like somewhere over here. Here's 4, here's negative 2. So that's the center of the ellipse. I will go out by 3 in the horizontal direction. So that means we're going to go out to this point over here, go out this point over here. So that's across by 3, across by 3. And similarly, we're going to go up by 4 and down by 4. So probably somewhere a little bit higher. So excuse the curve of my graph because, it's definitely not matching up to the scale that I would actually like then. Okay, but nonetheless, you get the idea. So here's x, here's y, and put it all together. So the curve, the ellipse we said is going to be this guy. And just like the first problem, what we're going to do is we're going to go ahead and think about t as time, so then that way we can see what direction does the point actually go then, if you were to assume that, again, there's like a particle that is going around this ellipse. So final step, let's go ahead and say t is equal to 0. That is going to yield for the x value, that looks like it's going to be 7. And y would then be equal to negative 2 plus 4 times 0. So that's going to be negative 2. So it looks like 7 negative 2. That means that this right here, that's my starting point. T is equal to 0. Now, taking the next one, and we really only have to do 2 because that'll give us an idea about this curve since it's circular. Let's say t is equal to pi over 2 then. So x is now equal to 4 plus 0. So that's equal to 4. And y is equal to negative 2 plus 4, so that is equal to 2. So that point is located over here, so that's when t is equal to pi over 2. And right there, now we get the idea then. So this is going to be going in a counterclockwise direction, right? Just like on the unit circle. And it's just going to be circular, going back and forth and so on and so on. And hopefully that counterclockwise thing makes sense to you because, again, looking at our setup, we have x is equal to some sort of function with cosine, y is equal to some sort of function of sine. So that tells me, hey, this is going to be kind of like a unit circle thing that's going on. Okay, last example over here. This one I want to, again, graph out what the parametric equation looks like. And unfortunately, we don't have a good identity that we can use with tangent and cosine of cosine squared of t. So for the trick for this one over here is, well, we're still going to have to isolate one of the variables over here. The first top equation, let's go ahead and draw a triangle for this, going back to pre-calc the first semester. So for this right triangle, we have the following. We can go ahead and say that tangent of t is equal to x over 2 if we divide 2 from both sides of the equation. Here, the ratio says that tangent, if t is going to be this angle over here on the side, the opposite is going to be x, and the adjacent is going to be 2, because tangent is opposite over adjacent. Knowing the opposite is x, the adjacent is 2, then we can solve for the missing side, which is now going to be the Pythagorean Theorem. So 4 plus x squared. Now, the reason why that helps is, now if you look at the second equation, well, that's in terms of t, which tells me, hey, we're referring to the same triangle. So in this triangle, we have to figure out what is cosine of square t. So underneath it, we can go ahead and solve for that. So let's see, cosine of squared t is going to be adjacent over the hypotenuse. So 2 over 4 plus x squared, and the whole thing gets squared. So that gives you 4 over 4 plus x squared then. Okay, take that and put it back in. So our final equation is now y is equal to 2 multiplied by 4 divided by 4 plus x squared. So that gives me a total of 10 over 4 plus x squared then. Okay, all right. Checking my math, make sure everything's okay, because I tend to make a lot of mistakes. Yes, I do. Oh man, right there, right off the bat. 2 times 4 is equal to 8, not equal to 10. So I do apologize for that one. Okay, so now let's go ahead and sketch the graph of this. And this graph is one that's not exactly familiar, but we kind of did it in the past actually. And the way we do it is by looking at the end behavior of this graph. So by end behavior, I'm saying what happens when x is approaching towards positive or negative infinity. And what you get then is y is basically approaching towards 0. So that is going to be our end behavior. Now, also looking at the characteristics of this graph, or this equation, I know that if I minimize x, then y is going to be as large as possible because x is in the denominator. So repeating that one more time, if x is a really small number, or as small as possible, then that means that y is going to be as large as possible. So that point is located at x is equal to 0. So y then is equal to 2 in this case. Okay. So putting it all together, let's see what that graph looks like then. So here's your curve. Let's see, 0, 2. So that's coming from over here. So here's 0, 2. And the equation itself, y is equal to 8 over 4 plus x squared. This is symmetric because you notice that whatever you put in for x, if you put in a negative value of it, it's going to give you the same value of y because of the x squared. Taking that along with the end behavior thing, and there's no vertical asymptote, the curve to me would then look something like this then. Okay, so that is going to be the bell curve, which is going to represent this equation. And final item, just like before, we're going to go ahead and look at what happens when I plug in values of t, so you can see how the how this is parameterized. Let's see here. Let's go ahead and make a substitution. I'm going to go ahead and erase some of this so I can make some space. Okay, so erase all this guy right here. Let's see. When t is equal to 0, we are going to get x is equal to 0. And y is going to be equal to 2, looks like. So that is telling me that we're starting at the top of the bell curve, which is over here. T is equal to 0. Next, we'll go ahead and plug in, let's say t is equal to pi over 4. So we get now x is equal to 2, and y is equal to 2 multiplied by 1/2, which is equal to 1. So that point is going to be somewhere over here. Okay, so that's when t is equal to pi over 4. So now that gives me an idea as to what the curve is doing. It's going towards the right this way. Okay. Now, as for the left-hand side, we can keep plugging in value for t just to see what happens here. So let's continue on with the adventure. So t is equal to pi over 2. X is going to be equal to undefined, or technically kind of like saying it's going towards positive infinity. but whereas y is going to be equal to 0. So that tells me, yeah, it is following the curve and it's going towards infinity then. So it's like getting closer and closer to the x-axis. Then we also have t is equal to, continue on, how about 3 pi over 4? We get x is equal to negative 2 in this case, and y is then equal to 2 times 1 over 2, which is equal to 1. So it looks like the next point that we have for 3 pi over 4 is located on the left-hand side. And that part, it actually is okay with me because this is telling me that the curve is going far as possible on the right, getting closer and closer to the x-axis. And as it passes pi over 2, which is kind of like asymptotic, then it appears on the left-hand side. And now it's going back to the origin point, of which is going to be t is equal to 0. So that is going to be my curve then. So everything is basically going towards the right. All right, so thank you again for watching, and hopefully you learned something. I will see you next time. Have a good one. Bye.